Okay, welcome everybody to today's talk. So first, an announcement. We're very happy to say that Michela Paganini from Facebook AI Research recently joined our team of organizers. If you don't know Michela, if you don't know her, she will be giving a talk in 2 weeks, so the next talk slot. So there she has a chance to introduce herself and you can get to know her area of research. Today, we have Lenka Zdeborova from very recently EPFL Lausanne. So sorry for that, the affiliation was incorrect in the announcement. She recently moved. Lenka did her PhD from Charles University and University of Paris in combination. Then she did a postdoc in Los Alamos and a CNRS research fellowship at University of Paris-Saclay. She received several recognitions for her work, including the CNRS Bronze Medal in 2014, the Philip Meyer Prize from ENS Paris, and the Irene Joliet Curie Prize for Young Female Scientists by the Ministry of Higher Education, Research and Innovation. So we're very happy to have Lenka with us today. And please, Lenka, we are looking forward to your talk.
Thank you, Fabian.
Oh, one more announcement. If you do have questions, please feel free to add them in the chat, and Lenka's student will be happy to answer them, or Lenka will address them in the end. Okay, go ahead.
Yes, that's correct. So indeed, the affiliation was not really your fault or anything. It changed only a week ago, and yeah, so it's really nice to be here to see this big crowd of people interested in the interface of physics and machine learning. That's something that I'm interested in for a long time. So today I will tell you about insights on gradient-based algorithms in high-dimensional learning. Some work that I have been doing in the past 2 years with the group of Florent Sakala, with whom we are developing in general these topics, and colleagues who are specialists on these dynamical questions, Pier Francesco Urbani, Giulio Biroli, Chiara Camarota, more recently Eric van den Eyden. But the really main people, as usual in these works, are the students. So my student Stefano Manelli Sarao, who is also in the audience. And so don't worry to ask some questions in the chat. He will be able to answer even during the talk. And more recently, Francesca Mignaco, who is continuing this line of research. So I start with the list of references on which this talk is based. So it's these 6 papers, 5 of them, you see the first author, that is Stefano, as I mentioned. And the last 3 are not published yet, but the first 3 kind of appeared either in PRX or in the machine learning conferences. So this talk will be about stochastic gradient descent, as this is the workhorse of machine learning. And so we need to understand basically how it works, why it does what it does, kind of in more detail that we so far do. And as you probably heard or might have heard in deep learning, despite some of theoretical works that would aim to show that in some suitable regime, there are no maybe spurious local minima in deep learning, actually in practice, the empirical observation is that local or even global minima with bad generalization error do exist. Yet, if you randomly initialize and run stochastic gradient descent, then you find good generalization minima. And the paper that is really nice, there are many papers, but here I pick one that I like that is nicely putting in empirical evidence this fact. So if you don't know it, check it. And so the question that we will try to answer, not yet fully today, but that's what we are aiming, is how does gradient descent algorithms or gradient descent based algorithms manage to avoid the bad minima? And our strategy will be the following. So the goal here is that we need to understand, so since there are bad local minima and gradient descent can reach them, in order to understand why from the random initialization the gradient descent is working fine, we really need to understand the whole trajectory of the gradient descent, not only the landscape, because that will not be enough. The second point here is that is in practice, that the number of samples in machine learning is usually limited and the constants matter, whether something takes 10 times longer or 10 times slower or less samples or more samples, it does matter. So this is again like setting what we aim for with respect to maybe the more theoretical computer science works, where often one would go after rates, not the constants. And sometimes the number of samples in the assumptions of the theorems would be just unreasonably big. But in order to be able to do that, to really keep the number of samples as small as possible and the constants in, we need to simplify somewhere. So the place where we do simplify, and where usually say theoretical computer science or theoretical learning theory does not simplify, is that we will assume something about the data. We will assume a generative model for the data as kind of a first stage to get insight into the behavior of the algorithms. So this is an approach that to physicists is kind of very natural, to first model the things and get insights and then go on from there. So the first such model, synthetic model for data that we will consider, will be the spiked matrix tensor model. So this is not yet even a neural network or supervised machine learning. This is a problem of unsupervised machine learning. So in, say, inference or machine learning language, I set this problem in the following way. I define a loss function that is a function of a variable x over which I will be optimizing. The variable x lives on n-dimensional sphere. Here I actually use n, but later in the talk it will be p. So what is capital N and what is small p, it's always the same. Oh, maybe not. Oh, I see. Here small p is something else. Okay, I think I messed up my notation. So here capital N will be the dimension of the sphere in which x lives. And then the loss function is a sum of two terms, squares of two terms, where one of them is x times its transpose minus a matrix, where the matrix was created, as is written below, from some ground truth vector x star plus Gaussian noise. And plus a similar term, where this time it's not just x transpose, but it's xi, xj, xk, etc., the tensor product of this of p of these vectors x minus a tensor t that was created again from the same ground truth vector x star plus a different noise with the given variance. And so the goal in such a inference problem is to find back a vector that is as close possible to x star as possible by minimizing this loss function L of x over x. And this might sound kind of abstract. This is called the spiked matrix tensor model. It's kind of broadly the spiked matrix model and the spiked tensor model. Both of them are studied in statistics, in computer science. To kind of approach to a physicist what this model actually is, if you write it slightly differently, here I just redefine these constants, these variances of the noises in a way that is commonly used in physics, but otherwise this is the same model. And instead of writing the loss function, I actually developed this loss function and realized that since the x lives on a sphere and these tensor t and matrix y are known, then these are just constants that I can put away, and minimizing the loss is the same thing as minimizing the function h of x lower here, down here, which I call x because you can think h because you can think of this as a Hamiltonian. And Hamiltonian of which model it would be, this would be the 2 plus p spherical spin glass model that is widely studied and well known in the statistical physics of disordered systems. The only difference with the model that is usually studied in physics is that in physics we would usually not have this ground truth vector x star that generated this quench disorder y and t. Whereas here, this quench disorder y and t is generated using this x star, and then the goal is to find it back. So you can think of this x star as a special spin configuration that is kind of planted into the disorder of the system, and that you're trying to find back by minimizing this Hamiltonian. But one point to make is that minimizing the Hamiltonian, of course, finding the ground state, that would correspond in statistical language to the maximum likelihood inference. And that's what we will be mostly looking at. The gradient descent is aiming to solve this. But it's also good to know that if we actually want to solve optimally this inference problem, then we should not be minimizing the Hamiltonian and finding the ground state or minimizing the loss equivalently. What we should be doing instead, and that's a little theorem, proven on page of every like Bayesian statistics textbook. What we should be doing instead is that we should write the Boltzmann measure corresponding to this Hamiltonian and sample it at temperature 1. So instead of looking at the ground state, temperature 0, we should sample uniformly at temperature 1, then compute the marginals, and the base optimal estimator is actually linked to the marginal at the temperature 1. And another name for sampling at temperature 1 or at some generic temperature, the algorithm that is well known in physics that actually does that is the Langevin algorithm. So we are guaranteed that on a finite system in infinite time, the Langevin algorithm will find uniform samples of that Boltzmann measure. But of course, infinite time in practice means exponentially large in the size of the system. And here we are focusing on non-convex problems. So of course, this loss function is highly non-convex because of the tensor part, and high dimensional ones because the dimension of the sphere, the number of spins, will go to infinity. So that's the dimension in the statistics language. So of course, algorithms that would run exponentially long in that dimension are not interesting. And we are rather interested where the Langevin algorithm will go in a constant time, or maybe at most constant times log of the size of the system, log of the dimension. And that's much shorter, of course, and that's the kind of relevant time scale. So that's what we will aim for. But before looking at the gradient descent or the Langevin algorithms, that will be the main topic of the talk, I just want to show you the phase diagram using kind of information theoretic tools and other set of algorithms that are approximate message passing algorithms that are not so widely used in like practical machine learning. That's why we are studying the gradient descent and the stochastic gradient descent. But just to give you like a first notion of how this model actually behaves. So the y and x axis are the variances, or one of the variances of the noises that you're adding to the matrix or to the tensor. So the delta p is for the tensor, delta 2 is for the matrix. So of course, the bigger is the noise, the harder it will be to find back this vector x star. So the bigger the two noises are, the harder it is. But you see in this phase diagram that kind of what matters more is the variance of the noise in the matrix, the delta 2. It needs to be smaller than 1. You need to be in the green region for the problem to be easy with that approximate message passing algorithm. If the noises are such that you're in the red region, then you cannot possibly find anything correlated with the vector x star. And if you're in the orange region and you had exponential time in the size of the system, then you would be able to find something correlated with the ground truth. But the approximate message passing is not able to give you anything correlated. And that kind of this M here would be the magnetization or the correlation with the ground truth. So the true one is positive, but the one given by this approximate message passing algorithm is 0. And without like really telling where these methods come from and what they are doing, this is what kind of the physics of disordered systems was developing for past 20 years. This is kind of what we know well. So take it. That would be for another talk. So this particular algorithm is actually conjectured to be optimal for this problem from all the polynomial ones. So if this one is not able to do it, then no other algorithm we think will be able to do it. So this is for comparison. And now we will be putting here the performance of the Langevin algorithm and the gradient descent. So you can kind of guess for yourself where it will work and where it will not work. Will it be as good as the approximate message passing or not actually? So just to define the gradient-based algorithms, so here, the vector x over which we are minimizing, just this derivative will be, this minus mu times x, which in machine learning would be called weight decay, and in physics, we could call it the spherical constraint, or it plays this role, minus the gradient of the Hamiltonian or of the loss function. And if we add a noise, just Gaussian noise with variance that is proportional to temperature, then of course, if temperature is 0, then the noise is not there. So then this dynamics corresponds to the gradient flow, not descent, but flow, because we will be switching to continuous time, because that's the case in which we will be able to analyze this dynamics. And if this temperature is 1, then we are back at the Langevin dynamics, at the Langevin algorithm, that, as I said, at exponentially large time is guaranteed to sample the posterior, but we are interested here at what happens at large constant times. So why did I pick that particular model, this mixed matrix plus tensor model? Well, because in the physics of disordered systems, that's basically the only one for which the dynamics of the Langevin gradient descent can be solved in a closed form. And this is well known from this work and series of work, but kind of the one that is most often cited is this work by Kuliandolo-Kurchan from the 90s, where for really close variant of this model, so again, the variant that doesn't have the X star, that doesn't have the planting, writes the dynamical mean field theory, which are closed form equations to actually track what the Langevin dynamics or what the gradient descent is doing. And these equations were actually proven later on in the mathematical literature. And so what we needed to do, we just needed to generalize them to include this X star, the planting. But that actually ends up to be pretty straightforward. So that's what we did in the first paper in my list. You know, this is just to, I don't know if impress you, but if you haven't seen these equations before, this is harder to understand, but if you know them, you will recognize them. So these are closed equations on these 3 variables, the autocorrelation of where the spins are between time t and t prime, the correlation between the dynamics state and the X star, and the response function R. So you define these 3 functions, and then you write these differential integral equations that actually close on these 3 functions. And you have, you know, I give you 2 sets of them, because when you take the temperature to 0, you know, it changes a little bit how the equations look like. So you have this case for the Langevin algorithm for temperature 1 and for the gradient flow for temperature 0. So I will not be giving details about how these are derived, but this is a pretty standard kind of you know, textbook derivation from the physics of disordered systems. So now, instead of looking how these are derived in detail, that would be more for a longer lecture, let's look how it behaves. So here I am plotting the correlation with the ground truth that is reached after the algorithm runs for a certain time for several different values of the noise on the tensor. So the bigger the variance of this noise, this delta is, the harder it is to find the signal. And you're seeing on the picture that the bigger the noise is, the smaller is the correlation eventually. So that kind of goes in the right direction. The harder the problem is, the smaller should be the correlation with the signal that you are looking for. But what is not intuitive is actually that the bigger the noise is, the shorter time it takes to get a good correlation that is kind of sufficiently away from 0. And for smaller noises, which should be easier, it takes really long time to get away from the 0 magnetization. So this is non-intuitive. And in the inset, I'm just for comparison plotting what the approximate message passing algorithm would be giving you, which goes intuitively, like the harder the problem it is, the harder it is for the algorithm. But the Langevin algorithm kind of in this respect behaves counterintuitively, but nevertheless, that's what it does. You can check with simulations, you see that that's exactly tracking the dynamics as theory said it should. And if you actually take this time it takes to go away from the 0 magnetization and extrapolate what would be the value of the noise so that this time goes to infinity, then you can go back to the phase diagram that I showed you and actually plot a line, which is here the dotted line, that splits this phase diagram into one additional region the kind of green-orange region, that for the conjectured best algorithm known on the market, this approximate message passing is an easy region, but the Langevin algorithm there actually gets stuck at no correlation with the signal whatsoever. And there is this critical point at 2 where this line actually joins this line at 1. So here we are seeing that the Langevin algorithm actually has harder time to solve this problem. And you can do exactly the same analysis. You write the equations, you run all the analysis for the gradient flow, and you can plot again the curve below which it will not work. And you see that this is even higher than for the Langevin algorithm. So the fact that it is worse than the Langevin is not surprising, because I said that the Langevin is aiming to solve the problem in a base optimal way, whereas the maximum likelihood in these high dimensional problems is not really optimal. So that it is worse is not surprising, but how do we kind of understand what is the gradient flow doing? So kind of without really thinking yet about it, the kind of popular explanation would be the following. So you have a region of parameters, and for each point in this phase diagram, there is a landscape corresponding to this optimization problem. And it could just be that as you are increasing the signal to noise ratio, that if you have a lot of noise, you are on the left here, then there are spurious local minima. And when the spurious local minima disappear, you only have the global one that you're looking for, then the algorithm works. So that would be kind of the first kind of guess, the notion that you would have in mind to explain that curve. So in this mixed matrix plus tensor model, we actually can analyze in very much detail not only the dynamics, but also the landscape, like how many of minima of what order there are. And this is something done with what's called the Katz-Rice approach that again is kind of widely used and known in the physics of disorder systems, but also in mathematics of studying non-convex landscapes. So again, I'm not going into detail of how this works, but just to show you that once you carry out this calculation, it gives you a pretty not so complicated closed equation that is describing of how many local minima there are at a given value of these two variances of the noise, at a given value m, which is the correlation with the ground truth, and at a given energy, so at a given value of the Hamiltonian. The Hamiltonian had two terms, the tensor term and the matrix term, so E2 and EP are these two terms in the energy. And when you actually plot what this expression means in, again, the phase diagram, it tells you that there is a line in purple here that I call landscape trivialization, above which there would be no spurious local minima, and below which there actually are exponentially many spurious local minima. And so you see that this popular explanation is not quite working here, in the sense that these two lines are not the same. The line below which gradient flow stops working is not the same as the line below which spurious local minima do exist. There is a considerable gap between the two. So how do we explain that? So to explain that, we need to think a bit more what's going on with the dynamics. And to do that, we actually look a bit more in detail of how the dynamics is proceeding to find this correlation with the signal. So in this picture, you would have the value of the loss or of the energy that the algorithm sees at any given moment at time as it is running. Again, for 4 different points in that phase diagram. And with the dashed lines, you would have the magnetization that it reaches at that time. And you're seeing here is that if the noise delta 2 here corresponding to the red and to the yellow curve, then the algorithm is stuck at some energy and stays there. And the gray and green curves here, they actually, after some time, that can be pretty long, get at lower energy kind of suddenly. And moreover, these plateaus that you're reaching, quite interestingly, these correspond to energies that are known in physics to be the ones where if you didn't have the X star, if you just had the good old mixed spherical spin glass, that's where the dynamics in that model would get stuck. And that is called in the statistical physics literature, the threshold energy. So the dotted line here is these values of the threshold energy. And you see that the dynamics in the planted model does basically two things. It kind of first, decays fast to the threshold energy, and then wants to stay there, but sometimes it escapes. And so once you kind of make a hypothesis that it goes to the threshold energy, and then basically what matters is whether these threshold minima are or not unstable towards the direction of the signal, then this is a way to understand analytically whether the algorithm will work or not. And what I just said in words, you can actually very simply put it in the equations. And here the first equation would be describing where are the threshold states. And the second really simple one would be describing whether the threshold states actually are or not unstable towards the signal or not, which you look at the Hessian of those threshold states and you see whether it has an eigenvalue that corresponds to an instability towards the signal or not. And the condition for that would be this one. And if you put them together, you actually have a condition when the threshold states will become unstable towards the signal. And if you plot that last condition into our phase diagram for the gradient flow, that would be the blue line. And you see that this one is kind of beautifully agreeing with the points that we obtain by solving numerically the dynamical mean field theory equations. And if you do, and moreover, it has this simple expression. And if you do the same for the Langevin algorithm, that's actually this green dotted line in this figure, it also has a super simple expression. And again, goes perfectly through the numerical points. So this is the right explanation of what is going on, but maybe like still to put it back kind of in that popular picture, like how do we correct it, is that actually the dynamics goes to these, not any spurious local minima. It tends to go to the highest ones. These threshold states are also the ones that are the highest ones. And what matters is whether those highest ones are stable or not towards the direction of the signal. And if they are stable, like in the leftmost part here, then the algorithm doesn't work. And if they are unstable, then even though there might still be spurious local minima at some lower energy, the algorithm avoids those and converges nicely to the optimal correlation with the signal. So that's kind of how this picture should be corrected, at least in this particular model. And so now I'm kind of hopefully somewhere in the middle of the talk. And so I just want to conclude what I told you so far about this spiked matrix tensor model in 3 points. So first, I showed you a closed form conjecture for the threshold above which the algorithm will be working, and that threshold is a specific constant in the setting of the model. And the question you might ask whether this theory and these insights are applicable not only for this spherical spin glass or this spiked matrix tensor model, but also for something that looks more like an actual neural network in actual supervised setting neural network. The second point that I told you is that gradient flow is worse than the Langevin algorithm, which by itself is not surprising, but both are actually worse than this approximate message passing algorithm. That, at first we kind of were not sure whether it's totally expected or not, but okay, this is what happens here. And you could ask whether there is some way to change the gradient descent into something smarter that would actually approach the approximate message passing threshold. And the third point is that the gradient flow sometimes work even when actual spurious local minima are present. And I showed you the mechanism of how that happens in this particular model, and we can quantify it with this Katzreis approach. And you could ask, what about stochastic gradient descent? Would stochastic gradient descent have the same problem? Because so far I didn't touch stochastic gradient descent at all. I was talking about gradient descent and gradient descent with noise, which is the Langevin algorithm. So a year ago, I would have stopped the seminar at this point because I didn't know the answer to these green questions. But today I actually have an answer to each of them. So that will be the second half of the talk and the second half of the 6 papers that I was citing at the beginning. So let's start with the first one. So is this kind of theory applicable to simple neural networks? So in statistical physics, when we, in the spirit of constructing a model, a synthetic model for data for which we can get analytical insight of how the learning is working, the most popular model is this teacher-student setting of the neural network. So it's this simple setting where you actually consider two neural networks. One is the teacher network, to which you feed data X, that you actually, in the simplest cases, you have n samples of p-dimensional data. Yeah, this is the point where I'm switching now. P is not the order of the tensor anymore, but it will be the dimensionality of the data. That's probably not the best choice for notation, but that's what it is in this talk, nevertheless. And in the simplest case, for this talk, this data will be just IID random. Every of the samples will be just IID Gaussian vector. And then you generate the weights, W star, that will also be IID random. Then you pick a neural network, like for instance, this one here, that I will call the teacher network, that generates labels Y. And then the student network observes samples of X and Y, n of them. X is p-dimensional. And you either can use the same architecture of the teacher network or not. This will actually be the I will do both in this talk. And the question you're asking is, can you learn the same function so that if I feed you new X's that were not in your training set, can you generalize properly? Can you generalize well? So if you, for instance, could learn exactly those value of W star, then you did your job. You can learn the same function by learning maybe different set of weights that are still representing the same function. So that is possible. So what you aim at is to learn the function, is to be able to generalize. That's kind of the goal in supervised machine learning. So this is a setting that, again, in the physics has been studied since the 80s. The simplest case and kind of most common would be the teacher-student perceptron, where the activation function the teacher uses is just a sign function. And what is important here is this high dimension limit, that the number of samples is going to infinity and the dimension goes to infinity, but with the ratio that is fixed. Whereas kind of the traditional statistics 20 years ago would always be considering the dimension p fixed and the number of samples going to infinity. So that limit behaves very differently from this kind of modern high dimensional, more challenging limit. But this perceptron model kind of doesn't fall in our category of trying to understand the gradient descent in non-convex. So high dimensional, yes, but not non-convex. If you're just cutting by hyperplanes, then you're still in convex. So to make it more interesting and non-convex, because that's kind of what I am interested, because then if you add hidden variables, deep learning is non-convex. So the simplest way, one of the simplest ways to make the problem non-convex is to actually, instead at the perceptron, look at what is called phase retrieval problem. So phase retrieval problem is widely studied and known in signal processing and imaging. It is super important in these domains. And here I'm kind of working with a model case of phase retrieval, where you can define this problem. It's usually not done as a in this setting with a teacher-student neural network, but you can define phase retrieval as a special case of this teacher-student setting, where the teacher is having no hidden units, and the teacher's activation function is the absolute value here. So the teacher takes a Gaussian W star, Gaussian data X, and generates the labels as the absolute value of the scalar product. And then the phase retrieval problem consists in this regression from the training data X and Y. Usually in signal processing, you actually want to recover the W star, but here we will be more in the kind of machine learning spirit. Rather than recovering W star, we just want to learn the same function and be able to generalize. So we are looking at the phase retrieval as a regression from the training data X and Y. And so then again, using kind of information theory tools and the approximate message passing, I can show you a phase diagram that actually comes from this paper. But as I said before, this would be for different talk, how these are obtained. I can show you what is kind of the optimal behavior of this phase retrieval for any exponentially costly algorithm and for the best known algorithm. So the any exponentially costly algorithm, that would be the orange curve in this figure, that is actually covered. Where you cannot see orange is because it's covered by the blue. So the mean square error that is closely related to the generalization error, I just maybe should have plotted it with the generalization error, but if I wrote on the y-axis generalization error, it would look exactly the same. And the x-axis is alpha, which is always in my talk, the ratio between the number of samples and the dimension. So this constant that you fix, you just have here, like 1 means that this dimension is exactly the number of samples, and bigger than 1 means that you have just fewer more samples than the dimension. And so information theoretically, as long as you have more samples than the dimension, you're able to solve this phase retrieval problem to 0 generalization error. You're just able to solve it perfectly. Whereas if you look at the performance of this approximate message passing algorithm, you need like 13% more samples than the dimension. There is this alpha AMP that is 1.13, that you need at least that to solve the problem perfectly. But now our question is, what about gradient descent? How does gradient descent do in this problem? So again, first, to talk about gradient descent, I need to define a loss function. So a natural loss function that corresponds to the phase retrieval problem, to the fact that the labels are just absolute value of the scalar product, would be the one written here. So you just take sum of square differences between square of the label and square of the scalar product. So that's if you think about it, that's a very natural way to kind of, if you find something that this loss function is W, for which this loss function is 0, you're solving the problem. So this is good. And then the gradient flow is written this way. Here we will, in this part of the talk, we will be looking at the weight decay such that the W is always lying on the sphere. So before we were doing that as well, but in the next part, we won't be doing that anymore. But this kind of just a detail into which particular case for which we wrote the equations. So this is an important graph. So here we are asking what is the performance of gradient descent in this problem, where I showed you that information theoretically you need alpha 1, approximate message passing needs alpha 1.13. You are probably asking what is known about the performance of the gradient descent or gradient flow. So the best paper, the best result that is out there in terms of how many samples is needed for the gradient flow to work is actually way far. It's not even alpha that is a constant. It's alpha that needs to grow as a polynomial of a logarithm of the dimension. And is the paper that I'm citing here. So on the other hand, this is fully, completely rigorous work. Everything comes with the proof. Whereas what I'm telling you is, at the level of kind of exactness of the theoretical physics. But for these dynamical questions that I'm talking about, we don't have proof of these results that I was showing you yet. So that's, that will be one of the challenges in the conclusions. But simply you see that there is a huge gap. There is a huge gap between what, where you could possibly hope the gradient descent would be working and where it is kind of proven that it is working. So the first thing a physicist should do is just simulations. Why don't you just try, right? You just run gradient flow or gradient descent for bigger and bigger system. So here actually N is P. I mean, what is capital N often in my talk is the same as small p. So here, that's exactly what we did. So there is a fraction of success where you find almost perfect reconstruction averaged over many rounds for different values of alpha, and alpha here is still the number of samples divided by dimension. And you see that as your system is getting bigger and bigger, and here we range from dimension 32 to dimension around 8,000, you see that there is some shift, but it seems to be saturating. It's kind of a numerical evidence for the algorithm working at some constant alpha, that it doesn't need this logarithmic alpha in the dimension. Okay, so you try to work with that hypothesis and kind of bring a theory that would establish something along those lines. So how you do that? So that's something that we do in this paper cited here. So first of all, you kind of, I was telling you about this 2 plus p spin mal, not for nothing. I just, that you try to take inspiration from there. You try to ask, okay, what worked there, will it work here? So there we saw that the gradient flow first goes to the threshold state, and then through an instability of the lowest eigenvalue of the Hessian, with a kind of a BBP-like transition from random matrix theory, it actually either that eigenvalue is there or not, and its presence is what drives the success or the failure of the algorithm to go towards that direction of the signal. So numerically, this is what this figure is showing. You can see that this is also true in the phase retrieval. So on the right, what I'm showing you is the energy or the loss that to which you go if you actually don't have the teacher, if there is no ground through W star. So that defines the threshold energy, just numerically a way to compute the threshold energy. Then I just take the value to which these curves converge and put them in the figure in which the lines this time are the runs of the gradient descent in the planted mal, in the phase retrieval mal. And you see that if alpha is big enough, then the gradient descent is working really, the loss is getting to 0 really fast. But if it is small, it's stuck at this threshold energy. And there is a transition from one behavior to another with kind of being stuck at the plateau for longer and longer. So numerically, the same kind of physics seems to be happening here. The trouble is that writing kind of the dynamical mean field theory is in a nice closed form as we did before, or the Gatz-Rice approach in a nice closed form as we did before is a bit more challenging here. So you can do things, but it's not so closed. But the argument that we had before actually can be generalized to this model. So that's what we do. So how did that argument go? So again, we needed kind of a random matrix theory result that would be able to describe the spectrum of the Hessian at the threshold states. And luckily for us, this this kind of random matrix theory result, exactly the one we needed, was actually provided in a recent work by Yuel Lu and student Li just last year. So we used their results. Then we assume the marginality of the threshold state. That means that the bulk of that Hessian is stuck at 0 eigenvalue. So that is a conjecture in physics. That's how these threshold states always looks like. And if we put these two facts together, it gives us a closed expression of alpha at which the gradient descent should be working, above which, should be working as a function of a probability distribution of the true labels and of the labels of the estimator that the gradient flow is currently estimating. And so this is something that you need to compute, this probability distribution, this joint probability distribution of these two labels. And the first point provides you an expression that if you had this probability distribution, then you have the threshold. Now the trouble is that we don't have this probability distribution exactly, but we can estimate it with the so-called one-step replica symmetry breaking theory, which is probably not exact. And you will see like one more evidence in one slide why it's probably not exact. But this figure here is showing you that it's not that much off either, in the sense that the left-hand side is showing you from numerics, there's the purple line, what is the threshold energy, and the black line is the 1RSP theory prediction of the threshold energy. And you see they're quite close. And on the right-hand side figure, you see moments of this distribution, probability distribution of the two labels, y and y hat. And you again see in lines theory and in points the simulations, and you kind of see that at least those moments agree. So if we plug in the probability distribution, the 1RSP approximation of it into our expression above, then we obtain a number for the threshold, which is 13.8. And so if you remember the simulations that they were saying something like 7, the 1RSP theory is saying something like 13.8. So there is quite some discrepancy. So we can still be pretty confident that this sample complexity actually is a constant that is not growing with logarithm of the dimension, that logarithm of the dimension is there because the proofs are so far, not strong enough to actually be able to get rid of it, but that the true is somewhere at the constant alpha. But we are not yet sure exactly whether it is closer to 7 or closer to 15.8. So what is the precise constant? We still don't know. But so that's so far what we know about gradient descent for this loss function that I was talking about. But you can ask, going to the next question in my list, how can the gradient flow be improved to approach the approximate message passing threshold? Is there some generic way to actually close this gap between the performance of the gradient descent and the approximate message passing, which is conjectured the optimal in those kind of problems? And this is what brings me, and the answer to that is something that maybe will surprise you, but it's something that is widely studied these days in machine learning, and that's the over-parameterization. So the conclusion of the next 10 slides, to give it ahead to you, is that over-parameterization is actually improving those thresholds. And the way to put our hand on that, so we again look still at the phase retriever problem. So the teacher is the same as before, nothing changed. This slide, you have seen it, and it's exactly the same slide. But now what will change is actually the loss function that I'm minimizing with the gradient descent. So I will be still talking about gradient descent in this part, or gradient flow in this part of the talk. But now the loss function, instead of corresponding to a kind of generalized linear regression, so a neural network with non-convex, non-trivial activation function, but no hidden units, that was the previous part. Here I'm looking at a loss function that corresponds to a neural network with one hidden layer and one very large hidden layer. So we need the hidden layer to be larger than the dimension. That's the condition for which the results that I will be showing you will be working. So that's the loss function that I wrote here. It's kind of analogous to the previous one, but you see that here the m, the little m, is playing the role of the number of hidden units in the hidden layer. And hence these w's, before I had one vector, one p-dimensional vector of w's, and now I have m p-dimensional vectors w's. So I have a whole matrix, whole first layer matrix of weights to learn. And then in the setting that I'm studying here, the second layer, I actually fix it to 1. And this will already be improving. So I could also learn it. That would be kind of a follow-up of this work. But here we fix the second layer to 1. And the first layer, we are fully learning it. And that's the gradient flow that we will be studying. So in a wide over-parameterized two-layer neural network. So this is something that we have done, again, with Stefano and Eric van den Eyden from NUIU in a recent paper. And here I just shooted you the theorem from that paper that is saying that if we consider a teacher with one hidden unit, so that's the phase retrieval. In that paper, we actually were considering a generalized teacher, but I will only be telling you about the results for the phase retrieval for one hidden unit or 0 hidden unit. That's the same thing for the teacher. And student that has number of hidden units that is larger than the dimension, so m bigger than d. D is the same as p. In this paper, d is p. Then kind of analyzing the landscape of this new loss function that corresponds to the over-parameterized neural network, we find that if alpha is smaller than 2, then this landscape has spurious local minima, and many of them. And if alpha is bigger than 2, then with probability that is bounded away from 0, that's what we managed to prove. But in practice, we actually believe that that means probability that is 1. Then the only minimum is the one corresponding to the ground truth values, to the solution that would provide perfect generalization. So here it is stated kind of more formally what I just said. But this is without any, so far without any notion of what the gradient descent will be actually doing. And to know what the gradient descent will be doing, that's a second part, that's a second theorem in the paper that is actually showing that in this over-parameterized regime, the gradient descent will be always finding a global minimum. So notably, for alpha bigger than 2, if there is only one global minimum and that's the right one, well, then the gradient descent has no other choice than to find this one. So this, putting these two theorems together, is showing us that the gradient descent in this over-parameterized regime should be working above alpha 2, equal to 2. And as a physicist, should always put like a simulation that we are actually having like all the constant right, and that indeed the simulations, as the dimensions growing, is doing what the theory is saying it should be doing, and it is. So if I put things together, again on this line, together with the results I told you previously, then I see that the gradient descent in the over-parameterized neural network is working starting from alpha equal 2, that is much lower than 7 or 13.8. Is not yet 1.13, but it's close there. So definitely, in this particular setting, we can reach this conclusion that over-parameterized neural networks needs fewer samples to learn the same function. And so this is kind of adding to this generic notion in deep learning that over-parameterization is good, that it's not hurting generalization. Here we kind of were thinking of perfect. What this axis means is when gradient flow is able to generalize perfectly in this particular phase retrieval problem. And so in the last maybe 5 minutes, I want to tell you about the third point. That is, what about stochastic gradient descent? So far I was talking about, there was no, so first of all, what is stochastic gradient descent? Who maybe not all of you are familiar with. So in general, we write always some kind of a loss function that is a sum over all the samples of a loss function of each of the sample. And the index mu here is indexing the samples, plus maybe some regularization, like in this case, a ridge regularization, lambda plus the norm of the weight squared, this weight decay term. And the stochastic gradient descent corresponds, to in the discretized setting, is the following update for the weights, where at every step time, that is eta here, you actually don't take the gradient of the full n samples, you only take gradient of one of them. So for time t, I take sample mu, and so the stochastic gradient descent. So now there are, in the literature, there are kind of two very different notions of how you do this. And sometimes they are not always, they are kind of clear which one is which one. So kind of the more theoretical notion of what is stochastic gradient descent is this online stochastic gradient descent, where at each iteration, you take a fresh sample and you never ever see a sample that you have seen before. And so that's called online stochastic gradient descent, or at least I call it online stochastic gradient descent. That's much of a simpler notion of an algorithm, because this one directly minimizes what's called population loss in the learning theory, and you don't have any generalization gap. The train error and the test error by definition is the same if you actually never ever see your samples again. But if you never ever see your samples again, then you also need a horrendous number of them. And in practice, this is not what's being done. In practice, this stochastic gradient descent is run multiple times through your data set. So that I would call it the multi-pass stochastic gradient descent. It reuses each sample many times. And in this setting, you have the traditional big difference between the train error that usually goes to 0 and the test error that is somewhere above 0. So that's the more relevant, definitely in practice setting, but also much harder to analyze. So there is much less of existing theory for this multi-pass stochastic gradient descent, but that's the one that we would like to understand. So can we generalize the dynamical mean field theory for this? So the first kind of question that you need to ask when you try to do that is actually, what is this gradient flow limit of stochastic gradient descent? Because when you think about it and you write the stochastic gradient descent in the form that I wrote it here above with the kind of blue S mu t, that would be a term that is taking care of the noise of the stochastic gradient descent, then the usual stochastic gradient descent would be when this S of t is 1 with some probability or 0 with some, 1 minus that probability. So that's the traditional way that stochastic gradient descent is done, where B would be then size of this mini batch that you're taking at every step of the descent. But when you think about it, this doesn't have a properly defined limit when the learning rate eta goes to 0. So you don't even know how to write the stochastic gradient flow in a straightforward way. And then the dynamical mean field theory kind of starts with the continuous time equations. So in order to define properly stochastic gradient flow, we kind of change the definition of the stochastic gradient descent, and we define this, what I call here the persistent stochastic gradient descent, where instead of at every time choosing a fresh subsample of your whole training set, you actually say, I define a stochastic process for each of the samples. I just define the rate for which I take the sample in and a rate for which I take the sample out. And there will be some persistence time, some typical time for which the sample stays in. And there will be some, batch size, that is how many samples on average there are at a given time. So this persistence SGD will be defined by 2 parameters, this tau, the persistence time, and B, that will be playing the role of the mini batch size. So that's the average number of samples that are in at any given time. And once you do it this way, then you can send eta to 0 and you have a properly defined stochastic gradient flow limit. So that's the limit with which we start. And then this B and alpha will be a constant, and all the other, D. Yeah, here there is also some D that should be P goes to infinity. So we do that. And then the model at which we studied this, this algorithm is actually a bit different than before. We take this classification of a Gaussian mixture clouds. So I define 2 Gaussians, or 3 of them, living in high dimensions, having a large variance so that they actually do overlap more than on the picture here. And then in the 2 cluster case, the labels are just one cluster is plus, the other is minus. But in the 3 cluster case, I actually put the peripheral clusters both at plus and the middle one at minus. This will define a data set that is actually not trivially linearly separable. So that's that one leads to really inevitably non-convex loss function. With the convex loss function, you will not be able to classify this 3 cluster data set. The 2 cluster data set, you can just classify it with just cutting by one plane. So that one is intrinsically not a non-convex. So that's the model for the data. And then about the dynamical mean field theory. So that's a harder case. We don't really have like nice, super nice closed form equations in this case, but we still have something that is useful to get some insight from. So it is based on this paper from 3 years back, by colleagues from the physics of disordered systems, Agoritas, Biroli, Urbani, and Zamponi, who actually, it's called equations for the perceptron model, but as far as I know, they were not really kind of so much motivated by machine learning, but rather than by dynamics of jamming or what's happening in glassy systems or in real structural glassy systems. So the perceptron they treat with this paper actually is not this teacher-student setting. There is no teacher, and the labels are not hence produced by the teacher, but are just random. So in a setting like that, you cannot really properly even define the generalization error, because if the labels are random, then you cannot predict them trivially. So we take their theory and we generalize it to the case that is the teacher-student setting, but that by itself is not so challenging. But we also generalize it to this stochastic gradient flow. And that's a little less straightforward. And the dynamical mean field theory does for us what it did before, is that it takes this coupled high dimensional system and actually rewrites it in terms of this time non-Markovian, so some stochastic system that will have memory, but only scalar one. So it will be a stochastic system on 1 degree of freedom with memory, non-Markovian. And that's kind of what it does for us. So if we follow the long derivation in that paper, here, there are just 2 slides with a lot of equations, but the main one is the one here for the H, the first one here. That's the stochastic equation for the kind of scalar stochastic process that is describing the dynamics in this high dimensional, strongly correlated system. And it comes in terms of this field H, and it kind of nicely shows you the sources of noise that you have in the stochastic gradient flow. You have a kind of effective Gaussian noise here, psi, that has a given covariance that is then self-consistently given by the rest of the equations. And then you have this lambda here, which was the regularization, plus some lambda hat, which tells you that actually there is some effective regularization coming from the stochasticity of the gradient flow. And then there is the term that has the ST in it, that is kind of explicitly the stochasticity of this persistent gradient descent. So when sometimes in literature we think like, oh, what kind of a noise is stochastic gradient descent actually introducing? This equation kind of tells you that. So that's interesting when you want to think about the physics. And then, okay, that's the main thing. And then there are, similar equations that once you solve those, you can extract everything as before, the correlation with the ground truth, the test error, the train error, what you want. So I'm at the end of the seminar. So just flash fast the results that you get. So these are mainly here to show, the lines that are the theory and the points that are the simulations match. And you can kind of deduce some interesting things from them, but I don't want to go over time. So I will just show you, it works, it matches, and this dynamical mean field theory actually follows the whole trajectory. And kind of, we studied, for instance, the role of the batch size and concluded that it's, playing a similar role as the effective regularization in this model. But I will go to the conclusions. That is, that this dynamical mean field theory tracks the trajectory of the gradient descent or gradient flow and the stochastic gradient descent or stochastic gradient flow for a range of synthetic data models. So that's kind of more than what we had before when for instance, in learning theory, one would show that gradient descent converges in some, say, convex setting. But rarely we see kind of results where the full trajectory is described from the random initialization towards where it goes. And obviously we have a lot of things to still do along these lines, deduce more insights from the dynamical mean field theory in terms of like how to set the hyperparameters, think more how to kind of put in evidence the nature of the noise, how different is it from the Langevin, etc. Think about other data models so that the input data are not always Gaussian IID. So this is another line of work that we are pursuing without kind of studying the dynamics in those models yet. But this is something that we want to now merge. And the third point is, I already mentioned that basically none of these results are rigorously proven, because showing even that these effective stochastic processes following from the dynamical mean field theory are actually exact is challenging in most of these cases. So this is something that, it's definitely a venue for future work more on the math or computer science side. And here I just put back the 6 references on which this talk was based and open to questions.
All right. Thank you very much, Lenka, for this great talk. I clap on behalf of everybody else. So other questions for Lenka?
I have a simple question maybe. So like when we look at deep networks, we often not use stochastic gradient descent, but other optimizers like Adam, etc. So have you any idea on how the picture would change for such optimizers? Whether you would get closer to optimal values, or is there any?
Yeah, so that's probably a point that I should have also added here. I wanted at some point, like, what about other more, more kind of advanced optimizers? So yeah, that's a very good question. I don't know. I mean, that should be in these points. I mean, we needed to start with the simpler ones. Of course, adding the momentum will add like additional memory to that whole, field theory. So that might end up challenging or not, but we didn't yet like dive deep into trying to do that.
Okay, I have an even simpler question in the same direction. So would you even know how to generalize your results for the stochastic gradient descent towards over-parameterized deep networks rather than over-parameterized wide networks?
So no, and that kind of goes to the direct. So on the dynamical side, yeah, I mean, maybe I should have said it. So the kind of only case where the dynamics has been tracked in detail for deep networks is for the deep linear networks. So that has really interesting dynamics, but then unfortunately kind of the fixed point where it goes, these networks are not expressive, so you cannot really like expect anything so rich from where you actually go, what you find as a function. So that's very limited. So of course we would love to be kind of, this is a step towards going to the deep nonlinear ones. But the reason for which kind of we are not really close to that yet is actually, this part of the talk where I was kind of skipping fast through it, saying, oh, there is some information theoretic analysis and analysis of approximate message passing that is kind of looking at a different algorithm, but kind of understanding what's going on with the learning curves and with the models. Even that one, we don't know how to generalize it to deep nonlinear networks. So if we could do that, so kind of to write a dynamical mean field theory, we first need to be able to write the static solution in a sense. So if we could write a static solution, then we could generalize to the dynamics. I'm positive about that, but we don't know how to write even the static solution for those. So that seems to be still far from reach.
Okay. And a second question, could you comment a bit more? In the end, you mentioned how the batch size acts as a regularizer. Can you
say it again? How the what?
How the batch size acts as a regularization?
Yeah. So yeah. So let me just go back into the picture because I just went so fast. So here it was simply an observation based on how the kind of dynamic, how the curve looks like, in the sense that in the 3-cluster case, we actually start at, the dynamics always starts at kind of being stuck at very bad error, just like random guessing, and then goes away from it. And the way the kind of position of the early stopping, so these curves here, this is smaller and smaller batch size, and this is changing the value of the regularizer. Lambda is the value of the parameter. So these are shifting because, of course, with smaller batch sizes, it takes longer. Whereas, nothing so much is happening in terms of when you see this go down. But in terms of where the early stopping criteria is, I mean, this smaller regularization kind of has good early stopping minima and then goes up to something not so good. And in terms of the batch size, we see a similar behavior. So this is kind of what we are kind of trying to put more, is it generic? Does it happen only in this model? Can we actually like see from the equation why this is happening?
Okay, I see. Are there further questions?
Hi, Lenka. Nice talk. I have a question about the earlier part of your talk. In this spin glass spike matrix model, there was this guess that you sort of put forward as the naive guess that one might have before you actually do the analysis, that you're finding global minima quickly because there are no spurious minima. And you had this Langevin curve and this gradient flow curve. And basically the upshot of your analysis, as I understood it, was that there's some spurious minima for which you still find global minima quickly. I was wondering if you could remind me what exactly is the nature of those spurious minima. The naive guess was too naive, you were saying, and then you had these beautiful curves that passed right through.
Yeah, let me really go back to that picture.
Yeah.
Yeah, so this is kind of the intuition behind that result. So we are talking of the middle phase here. This is the phase where there actually are spurious local minima, but you avoid them and actually find the good one. And what is happening there is that in the first stage, the dynamics goes to these threshold states. It goes, if they were, okay, they are not, in this phase, they are not minima, but if you were at smaller signal to noise ratio, they would still be minima. So the dynamics would get stuck here in these minima. It would actually never see the lower ones.
I see.
Because, everything is high dimension. So when I say like here there are 5 and here there are 4, you should really think there is entropy 5. There are like exponential 5 times n of them. So they are so much kind of, their basin of attraction is so much dominating everything that you always go to this ones. You never ever, you only exponentially rarely would actually hit those lower ones. So you always goes to the ones up there. So what matters is actually how the ones up there look like. Are they actually proper minima that make you stuck? Or are they actually saddles that drive you towards the signal?
Yes.
And that's what we analyzed actually. What is the shape of these high-lying minima? And the transition we have is transition between, are these like good minima or are these saddles driving you towards the signal? And at the point these are saddles driving you towards the signal, that's all what matters. Even if you still have spurious local minima lower here, their basin of attraction is completely subdominant. You never ever see them.
I see.
But of course, if you just do some kind of static analysis, just trying to count them, well, then they are there. You count them. And there are exponentially many of them. But their basin of attraction is completely subdominant.
So in this middle phase, I mean, basically you're saying that the dynamics basically never hits those spurious minima. It's driving you
exponentially rarely. Yeah, it would hit them exponentially rarely, but the dimension is infinite here. So that in practice is never.
So it's not about necessarily having a fast time scale of fluctuation out of the local minima. It's more that you just never hit them.
No, it's really law of large numbers where you actually with high probability are. And that's what's driving what you're doing.
I see. Whereas in the phase all the way to the left, you're going to get stuck up in the high guys because it's pretty likely that you actually hit them.
Yeah, you hit those and those are trapping you and you have no way to get out. And if you actually add noise and you're the Langevin, then you get out a little bit. So, you work at a little bit, the curve for the Langevin would be a bit more here.
I see. Thanks a lot.
Hi, I have a question. There's another line of work on analyzing gradient descent for deep neural nets where you can approximate them with kernel methods. So for example, the neural tangent kernel and things like this.
Yes.
The question is whether these kernel methods are comparable to the techniques in this talk or similar results.
Yeah, so the techniques are very different in the sense that at the moment you mapped the problem to a kernel method, you're back at basically very simple convex optimization problem. So at the moment you realize that in the lazy regime, the neural network behaves as a kernel method, you basically are done. There is nothing non-trivial with the dynamics because you're just like inverting a matrix. So you, in a sense, are in a regime of the learning where the non-convexity is completely irrelevant. It's not there. You kind of expand it around the convex part, in a sense. So you can think of this lazy regime or lazy limit or NTK limit as a small subset or small subspace of where the learning can be happening that is actually making the problem convex.
Is it correct to think of this as the, in the image it's shown on the screen right now, this is the trivialization regime?
Yeah. Yeah, I mean, yeah, in a sense, that's a yeah. If you kind of added that, if you added that axis into my phase diagram, which would be like, I don't know, in the Shizabach, this alpha, this kind of scale of the second layer. So you added that parameter and tuned it into the lazy regime, then yes, you would be going in a regime where trivially there is one single minima because this is just a convex problem.
Cool, thanks.
So that's, that's a like interesting line of work, but kind of my kind of first or second slide of wanting to study really the regime where the non-convexity strongly matters. It's that one is kind of going around that. And you have quite nice recent line of work showing that it's not expressive enough to learn very simple functions that actually a very, very simple neural network can learn. So that works by Andrea Montanari's work, but also others showing quite nicely that.
Okay. So while you're there, just out of curiosity, can you go 2 slides up?
Up.
Yeah, 20, yes.
This one.
Yeah. So does this actually hit the impossible phase at some point? Or does it asymptote?
This asymptotes. Yeah, so if the noise on the tensor was actually infinity, then it's like if you don't have the information from the tensor at all, like there is nothing. So then it completely reduces to the case if you only had the matrix. And if you only had the matrix, this is again a simple linear algebra model, because the whole trouble with the non-convex part of this loss function comes from the tensor. So if the noise in the tensor is such that it effectively is not there, then you're back at, looking at the spectrum of the matrix Y and seeing whether there is an eigenvalue out of the bulk or not, which is a very, that's the original BBP transition, very well studied problem. And so, yeah, these 3 curves, 1, 2, 3, would just go to 1 if delta P is infinity, kind of merging nicely with that well-known limit, where everything gets completely simple. But kind of, just to go back, it's interesting that the Langevin actually hits 1 at noise 2. There is a pre-critical point. So we don't really know why, but it's just the kind of curiosity of how these things look. So it kind of hits the trivial regime at finite value of this noise.
Where does the factor 2 in the denominator come from?
This 2 here. So yeah, I mean, I kind of expressed for a given, I mean, it's just simplifying this expression for t equal 1. So if I put t equal 1 here, and then I express the delta 2 in terms of delta 3 for p equal 3. P here will be 3. So
the fact that it's a 2
so
is
the
somehow...
2 comes from the 3 minus 1.
Okay.
Yeah. Yeah, so this is for p equal 3. So you would, in general, this would be the p minus 1 here. You could express it for a generic p, except that there is p here. It really becomes that simple for p3, but this is that pretty simple.
Okay.
I have a question about the matrix tensor model that you presented at the start. So like both the matrix and the tensor have the spike at the same target x, right? So like just for understanding where this toy model came from, why do you have both the matrix and the tensor? Like couldn't you have gotten by with one or the other?
Yeah, that's a good question. So if I only, so that's, yeah, I should have maybe spent more time, like say on a phase diagram of, for instance, this one. So if I only, so actually you can see what's going on with if I had only matrix or only tensor. So if I only had matrix, that would correspond when delta p is infinity. That's what I was just describing. So what would be going on? You would only have this impossible phase or this easy phase. And moreover, it's like a convex problem or linear algebra problem. So nothing so much interesting is happening there. If you only had the tensor, that means that delta 2 is very big, so that you're at 0 here. So that's the spiked tensor model that is kind of studied in several dozens of papers. But that one doesn't have the easy phase. It's either impossible or hard for all of the known algorithms kind of in the regime where theoretic transition happens. So in order for it to get algorithmically easy, you actually need to go to value of noise that scales differently than the information theoretic phase transition. And that's a regime where, for which these methods are kind of, certain things behave differently, and in some sense the AMP is not maybe the optimal one, or you need to redefine it. It's kind of a regime where this kind of analysis doesn't come up so naturally. So, and this actually happens for any p bigger equal to 3. And even if you are mixing, say, 3 and 5, it would still kind of be the same physics as here. You would not have the easy phase. So kind of mixing 2 and some p that is 3 or bigger is the only way to get kind of these 3 different phases. And it's kind of the presence of this hard phase that is indirectly driving the difficulty also for the gradient descent and for the Langevin. So that's kind of why we picked that peculiar mixture. That if as you were suggesting, if you had only one or the other, it would kind of be either simple or impossible.
So there have been some studies that try to derive spin glass models that are similar to this from neural networks. Have you or anyone else been able to get a model like this, sort of starting from a network and then making some approximations and arriving at?
Yeah, no. So yeah, I see the works you are referring to, but that's like a very, very drastic set of kind of assumptions and approximations to actually bring the neural network to that kind of model. Yeah. And I mean, you can kind of indefinitely argue about the assumptions, but for me, the result just doesn't make much sense, in the sense that, as I was kind of going in the second part of the talk, what is super important if you actually want to talk about something close to state-of-the-art neural networks, you need to have an optimization problem where the training error is 0 and the test error is not 0. So this 2 plus p spin model, or you can have a mixture or not, is not of that kind. This is not a supervised model where you can over-parameterize. So we were studying it to really get hand on the non-convex optimization and what happens if when gradient descent works but spurious minima are still there. But the landscape is very different from the landscape of the state-of-the-art neural networks. You really need this kind of setting where you can interpolate easily, training error is 0, and you are asking, is the generalization error still good? And those p-spin models are just not having that. So even if I accept these assumptions, the result is a landscape that is very different from how we know the landscape of deep neural networks looks like. So for me, this is not the way to go.
Right. Wait, how exactly is the landscape different? I thought the landscape was just describing the training loss only, not the test loss. So
yes, it was describing the training loss only, not the test loss. But the training loss also in these models has some non-trivial minima. Right? When I'm saying here that actually things work or don't work, it's not. Let me show one of the pictures where I actually have the loss. I had it here. It's not that the loss is 0. Okay, here it's like the Hamiltonian, so it's even like negative here. Okay, here it's not like a loss that must be positive, but there is. Great, because here I just subtracted some of those terms that were constant. But even if I kept them there, if I plotted the loss, what's going on there? Hold a sec. Yeah, there is some background noise here, but they don't know that I'm still in the Zoom. So I was saying, well, sorry, I just can't mute myself here. Why? I will just. Hey, I'm not done. Flo. I'm still in the talk. You're making a horrible noise. Sorry. Yes. Okay, sorry, I'm back. So it's different in the sense, I would, to describe this interpolation regime where the loss is 0, I wanted to go back to the loss, this one. So even if I was actually plotting this loss, the values at which the dynamics converges is not at all 0. And it kind of cannot, because these noises here are too big. So in a sense, I'm not hitting this interpolation regime where I would have a very, because of the over-parameterization, I would have a very wide area of global minima at 0 loss. These p-spin models are just not doing that. So in this sense, the landscape is not good. Like, you should really think of the landscape of the over-parameterized neural networks, and all of the state-of-the-art ones are over-parameterized. Not really in terms of a minima. Maybe you can be blocked at some like high training loss minima, but that usually doesn't happen. You go to 0 training loss. And the question is, how does the landscape of the 0 training loss look like? And you know that in that landscape, there are some points that are generalizing badly and some of them that are generalizing well. And you need to understand how comes that you always goes to the ones that generalize well and not to the ones that generalize badly. But this spherical p-spin model just doesn't have this type of landscape. So I'm just not seeing how that could explain this kind of generic observation.
Yeah,
it's still an interesting model to kind of, a playground for like how non-convex optimization looks like in general, kind of without thinking of deep learning as the main goal. So that's for sure true. And that's why it has been so much studied in physics and math and, broadly. But the landscape doesn't look like the landscape of the deep networks.
Thanks, that's really helpful.
Okay, we're approaching 7:30 at least in Switzerland. So I'd say we thank Lenka again for a great talk. And,
thanks to all the questions and your attention.
Thanks for sticking around for so long and answering them. And
yeah, sorry for the noise at the end. My kids came back and they didn't know I'm still on the talk. Usual thing.
All right, thank you.